In the previous chapter, we got a lot of information about transactions and the various consensus mechanisms in Substrate. And in this chapter, we will build up on our knowledge of Substrate by delving into the concepts of state transitions and storage, and then learning about concepts around accounts, addresses, and keys, and then learning about all the off-chain operations, and then finishing it off with some more information on cross-consensus communication. So let's get started. In this section, we will learn how the transactions taking place on Substrate are stored in the database and what types of storages are used. Key value databases. Substrate implements its storage database with RocksDB, a persistent key value store for fast storage environments. It also supports an experimental parity DB. The DB is used for all the components of Substrate that require persistent storage, such as Substrate clients, Substrate Lite clients, and off-chain workers. Try abstraction. One advantage of using the simple key value storage is that you are able to easily abstract storage structures on top of it. Substrate uses a base 16 modified Merkle Patricia to provide a trie structure whose contents can be modified and whose root hash is recalculated efficiently. Tries allow efficient storing and sharing of the historical block state. The trie root is a representation of the data within the trie. That is, two tries with different data will always have different roots. Thus, two blockchain nodes can easily verify that they have the same state by simply comparing the trie roots. And this concept is known as trie abstraction. Querying storage. So blockchains that are built with Substrate expose a remote procedure call server that can be used to query runtime storage. When you use the Substrate RPC to access a storage item, you only need to provide the key associated with that item. Substrate's runtime storage APIs expose a number of storage item types. This makes it extremely easy to access or query the storage and is one of the features that makes Substrate so popular. Now let's learn about accounts, addresses, and keys. An account represents an identity, usually of a person or an organization that is capable of making transactions or holding funds. Although accounts are most often used to represent a person, that doesn't have to be the case. An account can be used to perform operations on behalf of a user or another entity, or to perform operations autonomously. In addition, any single person or entity could have multiple accounts for different purposes. And in this section, we will learn a bit more about this. In general, every account has an owner who possesses a public and a private key pair. The private key is a cryptographically secure sequence of randomly generated numbers. The private key generates a random sequence of words called a secret seed phrase or mnemonic. The secret seed phrase is important because it can be used to recover to an account if the private key is lost. You may have experienced a seed phrase when you signed up for a wallet such as MetaMask. An account is usually defined as a public address with a public-private key pair. But in runtime, there's a small difference. And it's important for us to know how it works to avoid confusion in the future. In a runtime built with Frame, an account is defined as a storage map with a 32-byte address identifier and corresponding account information, such as the number of transactions the account has made, the number of modules that depend on the account, and the account balance. With Substrate, different chains can implement different rules for how accounts and the keys that control them are used, and these are called as specialized accounts. In most cases, specialized accounts are implemented in the context of a specific Frame palette, either in a pre-built palette like staking or multisig, or in custom palettes that you design. There are usually two types of specialized accounts. Multi-signature accounts. Typically, an account has one and only owner, and that owner holds the private key for signing transactions. The multi-sig palette enables you to configure a specialized account for executing transactions that multiple account holders must approve. And proxy and keyless accounts. The proxy palette provides another way you can configure specialized accounts for a Substrate-based chain using Frame. With proxy accounts, primary account owners can designate one or more other accounts to act on behalf of themselves. Proxy accounts can be used to add a layer of security by isolating primary account funds from accounts assigned to specific roles that can complete tasks on behalf of the primary account. Off-chain operations. There may be instances where you want to query off-chain data and utilize it, and the conventional way of doing this is by using oracles. But there is a limitation to the security, scalability, and infrastructure efficiency that oracles can provide. Substrate provides us with a few features to make it easy for us to support off-chain operations. Off-chain workers enable you to move tasks that might require more time to execute than allowed out of the block processing pipeline. Any task that might take longer than the maximum block execution time is a reasonable candidate for off-chain processing, such as website requests and random number generation. Since off-chain workers work with data that's off-chain, they need a way to store the information, and that is why we have off-chain storage. which is storage that is local to a substrate node and can be accessed by both off-chain workers and on-chain logic. Off-chain workers have both read and write access to off-chain storage, and on-chain logic has write access through off-chain indexing but doesn't have read access. On-chain state is expensive because it must be agreed upon and populated to multiple nodes in the network. Therefore, we have off-chain index, an optional service that allows the runtime to write directly to the off-chain storage independently from off-chain workers. The off-chain index provides temporary storage for on-chain logic and complements the on-chain state. Cross-consensus communication relies on a message format, XCM, that is designed to provide a generalized and extensible set of instructions for completing transactions across boundaries created by different consensus systems, transaction formats, and transport protocols. The XCM format expresses the contents of the message. Each message consists of a set of instructions being requested by a sender that can be accepted or rejected by a message recipient. In this section, we will learn about 4 concepts: the type of message protocols available, the properties of the messages in the XCM format, and 2 things that XCM depends heavily on: location and assets. So let's get started with message protocols. In the Polkadot ecosystem, there are 3 main communication channels. The message protocols used to transport messages between chains, which is upward message passing, enables a parachain to pass messages up to its relay chain, and downward message passing enables the relay chain to pass messages down to a parachain. Cross-consensus message passing enables parachains to exchange messages with other parachains that are connected to the same relay chain. There are 4 important properties of the messages that use the XCM format. Messages are asynchronous, they are absolute, asymmetric, and agnostic. XCM needs a way to express locations in a general and unambiguous way. For example, XCM must be able to identify the location for the following types of activities: where an instruction should be executed, where an asset should be withdrawn from, and where an account to be received assets can be found. For any of these activities, the location might be in the context of a relay chain, a parachain, a forwarding chain, an account on a specific chain, a specific smart contract, or an individual pallet. Most blockchains depend on some type of digital asset to provide economic incentives that are crucial to the security of the network. Some blockchains support a single native asset, other blockchains allow multiple assets to be managed on-chain, for example, assets defined in smart contracts or non-native tokens. There are also blockchains that support non-fungible digital assets for one-of-a-kind collectibles. For XCM to support these different types of assets, it must be able to express assets in a general, flexible, and unambiguous way.